Our title today is Electronegativity and Bonding. Electronegativity is a property of atoms, and like atomic radius and like ionization energy, we can identify trends in the periodic table for electronegativity. Okay, so what is electronegativity? The electronegativity scale tells us how strongly an element can attract an electron compared to another element. So the electronegativity scale is relative, okay? It is comparing one to another. It's relative to another element. And so we don't have an absolute scale of electronegativity in terms of a unit that is associated with electronegativity. It is basically just this element compared to this element, how strongly can it attract an electron. Now I want you to think about it in a minute and think about, well, what are the things that would make one element more electronegative than another? Where on the periodic table do we find elements that have very low electronegativity? Where on the periodic table do we find elements that have a very large electronegativity? Okay, I'd show you a table of electronegativity values right now, but I would be breaking copyright, and so I can't do that. Tomorrow in class we'll look at our books and we'll see some actual values, one element compared to another for electronegativity. So the question I would ask of you at this point is, here's our periodic table with its flashing purple light. So where do you think they're the most electronegative? Do you think that francium down here has a really, really great ability to attract an electron to it? Do you think neon has a great ability, a large electronegativity? It's able to attract electrons to it? Fluorine? What do you think? In general, electronegativity increases as you go across a row on the periodic table and up a group. So, this should come as absolutely no surprise to anyone. Francium has no ability to attract an electron to itself. Okay, its valence electron, its space for another electron is so far away from the nucleus. That nucleus is shielded so much by core electrons. Francium has no ability to attract electrons to itself. Pretty much like all the metals, right? They don't have the ability. Their valence electrons are held very loosely by the nucleus, and so there's nothing that's pulling them in. Right? Whereas as we go across in a row, what happens? Ooh, effective nuclear charge getting bigger. Bigger, bigger, bigger. Finally, when we get to group 7, the halogens, okay, tremendous electronegativity. What about neon? No, none. Does it have a place to attract an electron to? No, it's got a complete valence shell. So we're talking no electronegativity here at all. No ability to attract electrons because it's filled up. Nowhere for the thing to go. So our most electronegative element is fluorine. Least is going to be down here with francium. Okay. So as you go across, it increases, and as you go up a group, it increases. Or if you want to say it decreases as you go down, that would be fine too. The same thing. All right, so then hopefully you are already seeing the way that an element's electronegativity is going to affect its bonding characteristics. And the kind of bond that two atoms engage in is going to very much depend upon the electronegativity of each of the atoms involved in the bond. And so we like to say that bonding really occurs on a continuum based upon the difference in electronegativity between the two bonded atoms. So the electronegativity scale can be used to determine the nature of a bond. So if there is a large difference in electronegativity, one atom is going to be able to rip an electron away from the other one. If their electronegativities are pretty similar, then they are going to share electrons. Nobody's going to be able to rip an electron away from the other. All right. So, we're going to talk about 3 bonds here. First of all, we're going to talk about a non-polar covalent bond. Now, polar means that there are poles. There's a positive pole, there's a negative pole to the bond, meaning that one end of the bond, one of the atoms of the bond is positively charged, the other atom that's participating in the bond is negatively charged. Okay, it's polar, opposite poles on opposite ends. So a non-polar covalent bond means that there are no poles between this bond. The electrons are shared equally. Who recognizes this scale? We'll just get rid of that for now. All right, so you don't see values for electronegativity right now in this movie, but you will tomorrow. So if the 2 atoms that are involved in the bonding have no difference in their electronegativity, or up to a value of 0.5 difference in electronegativity, we basically say that they are sharing electrons equally, that the bond is non-polar, meaning that the electrons are going to be around each atom equal amount of time. So for instance, an example of a non-polar covalent bond would be, for instance, Cl2, chlorine gas. We've got a chlorine bonded to a chlorine. Okay, these are identical elements. They have identical electronegativity. And so, because of that, right, the difference between their electronegativity is going to be 0, and the pair of electrons that chlorine shares is going to spend exactly the same amount of time around this chlorine atom as they will around this chlorine atom. In simplistic terms, let's think about it that way. Or we could say that the negative charge is distributed. The cloud of negative charge is distributed equally between the two. Neither of these elements can overpower the other. They are doing the perfect sharing, the picture of a perfect kindergarten pair, right? Sharing equally that pair of electrons between them. Okay, so this is a nonpolar bond because the electron spin, the overall negative charge is equal between the two of them in terms of their pair of sharing electrons. Now, this is the same always when we have identical elements. Another one that is really important that we keep in mind, that is also a non-polar covalent bond, is a carbon-hydrogen bond. And this is important for lots of things that we will talk about here next month. Their difference in electronegativity is less than 0.5. I think, I'm not looking at my sheet right now, I think it's like 0.45 or something. And so we say that the carbon-hydrogen bond is also nonpolar. So even though they are not identical elements, these two atoms share their electrons equally as well. So very important, the carbon-hydrogen bond is a nonpolar bond. They share their electrons equally. Okay. Now, we also have a polar covalent bond. So, I'm sure you can't see this because this is in pencil. So, it's a covalent bond. So yes, they are sharing one pair, two pairs, three pairs of electrons. But these are not the picture of the perfect kindergarten pair. Okay, they are not sharing equally. They are bad sharers. Okay, so the electrons, the pair of electrons, are actually staying around one of the atoms more than the other. Okay, they're still sharing, but we say that it's polar. There's poles, and I'll show you in a minute what I mean by that. So, we say that the difference in electronegativity is less than 2.1, right, but it's going to be greater than 0.5. So, for those of you who are having a hard time seeing the pencil, it is 0.5 to 2.1. If the difference in their electronegativities are between these two values, then we say that it's a covalent bond. They're sharing electrons, but they're not sharing them equally. Okay, if they have a big difference in their electronegativities, one of those elements, the more electronegative of the elements, is going to have the electrons around it the most. Now, what are some examples of some polar covalent bonds? Well, let's do an important one here. Let's do the oxygen-hydrogen bond. Oxygen, hydrogen. Okay, if we use the periodic table, you guys, okay, we compare, there's hydrogen, and there's oxygen. Okay, oxygen is going to, it's further over here, it's actually going to have a much greater electronegativity. How much of a greater electronegativity? Oxygen has an electronegativity of 3.44. Alright. Oxygen is 3.44. No units. Hydrogen is 2.10. Right, so the difference between the two is 1.34, right? So their difference is equal to 1.34. So this puts them in the category of a polar covalent bond. Okay, non-metal, 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 so we know that they're sharing a pair of electrons. Now, because oxygen has this greater electronegativity, okay, this is going to be a polar bond, meaning that, okay, it has a greater electronegativity, it's going to attract the electrons to it more strongly. So we're going to say that the oxygen is electronegative, and the hydrogen is electropositive, right? So it's a polar bond. It's got two poles. It's got a negative pole and a positive pole. And what that tells us, you guys, is the pair of shared electrons, that cloud of negative charge, is sitting over here more than it's sitting over here. It's localized more here than it is here. So this bond has poles, a negative pole and a positive pole. And in simplistic terms, you guys, it's okay to think of it that these paired, the sharing of this pair of electrons, the electrons are going to spend more time around the oxygen than they are around the hydrogen. A polar covalent bond. They're sharing. Oxygen can't totally overpower hydrogen and rip away its electrons for good, but it keeps the electrons around it, the pair that they're sharing, more often. Okay, so that's polar bond. Now, the most polar of bonds are ionic bonds. And there's no sharing involved. This is the selfish child and the poor child that has to sit next to them in kindergarten, right? The selfish child does not know how to share. It just steals all the time. Takes, takes, takes. Okay, so in an ionic bond, there is no sharing of electrons. Valence electrons get transferred from the least electronegative to the most electronegative. The least electronegative, of course, being the metal. The most electronegative being the non-metal. So the non-metal just takes the electrons away and keeps them for good. And so now we've got a positively charged cation, negatively charged anion, and that's that positive and negative that hold those things together. All right, so anything that's got a difference in electronegativity of greater than 2.1, we are going to classify that as being an ionic bond. But, you guys, it's easy. It's metals versus non-metals. The difference between a metal and a non-metal is going to be greater than 2.1, as you will see tomorrow when we're looking at the graphic. And so we can still use our overall guidelines for determining whether you've got a covalent or an ionic bond, metal, non-metal, or non-metal, non-metal. But what we've kind of added to this idea is that really bonding is a continuum based on differences in electronegativity. And we will see that there are some gray areas. For instance, 0.5. What do we call it? Non-polar? Polar? What if something is a 2.1? Well, is it ionic? Is it covalent? You know, can we absolutely make the determination of 2.1? So tomorrow, you guys, we will address those things